Now today we shall discuss about the moment of inertia. We shall define it, okay, and which are the factors on which moment of inertia depends. Its unit dimension formula is discussed in this particular question. Now see, as you know that if you have ith particle, that of the rigid body, then its linear speed, that is v I, is given by Ri omega. Now see, omega, that is angular speed, and angular speed is constant, that of all the particles. Try to understand the motion of the, say, what you call it, seconds hands of the clock. All the particles, this will move this way, then the particle here also moves simultaneously. It will not remain behind, or it will not go faster, okay. So they will move simultaneously, so their angular speed omega is constant, okay. That is why if you have ith particle, then its angular speed will remain omega only, and it can be written as, or rather we can say linear speed can be written as vi is equal to Ri omega, okay. Now kinetic energy, as you know, 1 half mi vi square. Instead of vi we write Ri omega, so it becomes Ri square omega square, okay. And if you take omega square out of this, or rather we take all the particles and total kinetic energy of the system is taken, then the kinetic energy can be written as 1 half omega square is taken out, and here all the particles, means first particle, second up to n particle we take, then it becomes m1 r1 square, m2 r2 square up to mn rn square, and in the short form it is written as sigma mi Ri square, okay. So it is written as I is equal to 1 to n sigma mi Ri square, okay. So every particle which are having mass mi and distance from the axis of rotation is Ri. Try to understand, if you have this rigid body, and if this is the axis of rotation, and this is first particle, then its distance from the rotational axis is, say, r1, and its mass of this particle is m1. If you have second particle here, then say its mass is m2, and this distance is r2, okay. This way, if you have n particles, then this Ri omega square into mi can be represented this way. Here 1 half and omega square are taken out of the summation. If you have n particles, then omega is constant, then total kinetic energy of all these particles, here 1, 2, the third particle, fourth particle, and n particles are there, then total kinetic energy of the system of n particles can be 1 half omega square, and then this can be written as sigma I is equal to 1 to n mi Ri square, okay. Now K is the total kinetic energy of all the particles, and here whatever is there in the sigma, that is I is equal to 1 to n, okay, mi Ri square, is known as moment of inertia. So in general we can say that moment of inertia, capital I, is m1 r1 square plus m2 r2 square plus up to plus, it becomes mn rn square. So this becomes moment of inertia, this part, okay, where m1, m2, m3 up to mn are the masses of all the particles which are there in the rigid body, and r1, r2 up to rn are the distances, rather perpendicular distances from the axis of rotation, and this summation which we are getting is called the moment of inertia, which can be represented here in this way, okay. It is very easy to understand. Now there is a clarification about this moment of inertia, okay. Definition of moment of inertia. the sum of the terms obtained by multiplying the masses of individual particles of rigid body with the square of their respective perpendicular distance from the specific axis or rotational axis is nothing but the moment of inertia. It depends upon position and orientation of the axis of rotation. Try to understand. If you have a particular rotational axis, okay, say for example, you have a rigid body, okay, you have this rigid body, okay, and you have this rotational axis, and if you consider this as a particle whose mass is m1, then its perpendicular distance is r1. Now instead of this rotational axis, if I have a different rotational axis, I do not want to rotate about this axis. Now if I change the rotational axis, if I do not want to keep this as my rotational axis, okay, then I must have a different rotational axis, okay, I will have a different rotational axis. So the perpendicular distance of the particle from the rotational axis will change. Say this is my rigid body as it is, but now I have this as a rotational axis, I want to rotate in a different way, then this perpendicular distance of the particle is different. Then we can say the moment of inertia m1, r1, all the distances. Now for r2 the distance will be different, for say third particle third distance will be different. Okay, earlier this was my rotational axis, so these were the perpendicular distances. If I have this particle here, then this was the distance. Now this is my rotational axis, so now distance of all these particles from this rotational axis is changed. Therefore moment of inertia depends on the rotational axis. Very important, that is why this much clarification I have done. Okay, so moment of inertia depends on the position and orientation of the axis of rotation. Then it depends also on shape, size of the body and the distribution of mass of the body about the axis of rotation. Okay, moment of inertia is independent from their magnitude of angular velocity. Here there is mr square or miri square. Okay, it is not depending upon the angular velocity. Okay, mass is a inertia of linear velocity. Mass behaves as an inertia. If you have a 20 kg object and 50 kg object, then the inertia of 50 kg is more than 20 kg. Here moment of inertia is behaving similarly as that of the mass behaves in linear motion. Okay, so inertia for rotational motion is moment of inertia. Okay, so moment of inertia is providing the inertia for the rotational motion. We have P is equal to mb for linear velocity or linear motion rather. P is equal to mb. So here, and we had F is equal to ma. So here the angular momentum will become, instead of m we shall write I, instead of v we shall write omega. So it becomes L is equal to I omega. Okay, same equations, but their notations are changed according to the type of motion. Force is I alpha, instead of m we are writing I, and instead of a linear acceleration we write angular acceleration alpha. Okay, the role of mass in linear motion is similar to role of moment of inertia in the rotational motion. In SI units you can very easily say it is MIRI square. I is equal to sigma. Okay, mass is measured in kg, distance is measured in meter, so kg meter square, or joule second square, not used much. Okay, m1 l2 is the dimensional formula. Okay. Now we want to calculate the moment of inertia of thin and one thin rod is there. Okay, find the moment of inertia of thin and massless rod about the axis passing through its center of mass of rod, and pair of mass is suspended on both the ends of the rod. Try to understand this part. Whatever rod which we are having is not having any mass. In an ideal situation, this rod is having a negligible mass, or we can say very light. But here, mass is attached. Okay, two masses are, or we can say two spheres are attached at the two ends of this rod. Here the mass is m by 2, here also it is m by 2, this is its center, and we want to rotate it in this direction. Okay, the distance is here on both the side will be same because center is at midpoint, so L by 2 are the distances. Okay, now we want to calculate this, very easy. Okay, we have two particles, so it is a two particle system, and the distance of these particles from the center is L by 2. So first particle m by 2 and its distance is L by 2, so square of this, plus second particle same mass and L by 2 square. Okay, so that is written here. Okay, now easily we can simplify. Okay, it is 2 times m by 2 L by 2 square. Okay, 2 times m by 2 into L by 2 square. You can simplify this and get the answer. Okay, this 2 will be cancelled out, so it will be ml square by 4. Okay. Now we talk about the radius of gyration. See, this is a rigid body which is shown here in the figure. Let me try to show it to you properly. Okay, here there are different particles whose masses are m1, their perpendicular distances are r1. Second particle m2, then its perpendicular distance is r2. Similarly, third particle whose mass is m3, distance is r3. And nth particle, then mn, rn are the respective quantities. Mn is the mass of nth particle and rn is the perpendicular distance of nth particle from the axis of rotation. Okay. Now, as you know that there are n particles and their masses are different we have taken. Now, if you take m1 is equal to m2, બધા particle mass is સરખા છે, which are same masses. Okay, let the mass of each particle is m, then total mass of this rigid body will be, if there are n particles, then it becomes n into m. Okay, so that is given here. If their masses are same, then total mass is m into n. Now if you want to find the moment of inertia of this system of n particles, then this is our general formula, m1 r1 square plus m2 r2 square plus up to plus mn rn square. But instead of m1 m2, because their masses are same which we have taken, so all the masses are same, so it is replaced by m. M is taken common. Okay, and then it is multiplied and divided by n number of particles. Okay, here we are multiplying by n and dividing by n, so it is replaced or written in this way. Okay, here this m into n will become total mass, so we can write it m, and this quantity, okay, this quantity in the bracket, this quantity is replaced by k square. Here mn is total mass, so it is replaced by capital M, and this is taken as, suppose it is taken as k square. Okay, and k square is nothing but average r square. Average r square. Square of distances and divided by total number of particles, so it will give you average of r square. Okay, k square denotes the mean of square of perpendicular distance of particles of the body from the given axis. We have taken the mean. When we divide by total number of observations or total number of particles, then this becomes average. But it is the average of square of perpendicular distances of the particle of the body from the given axis. So this value is nothing but average of square of perpendicular distances of all the particles of the body from the axis of rotation. So we have replaced this as k square, and I is equal to mk square. And if you take the square root of this k square, that is k, then k is a geometric property of the body which is performing rotational motion, and this is known as radius of gyration of body about the axis of rotation. Okay, so if you take the square of this, the square root of this, then that will give you the radius of gyration. Okay, that is called the radius of gyration. Okay, the radius of gyration of the body about the axis defined as the distance from the axis of mass point whose mass is equal to the mass of whole body and whose moment of inertia is equal to the moment of inertia of the body about that axis. This is the meaning. What is radius of gyration? Radius of gyration of the body about a axis of rotation as a distance from the axis. Now try to understand this point, distance from the axis. You have this axis of rotation. You consider a particle whose mass is equal to the mass of this rigid body. Mass of rigid body is m, which is equal to n times m. Then say this is your rotational axis, this I have shown this same rotational axis. Now you consider a particle whose mass is m, which is equal to the total mass of the rigid body, which is at distance k from the rotational axis. And the moment of inertia of this is same as that of this particular rigid body, then this distance k is known as radius of gyration. You are representing the whole body as a particle whose mass is same as that of the body, and the axis of rotation is also same that of the original our rigid body. Okay, and the distance is taken as average of square of all the distances of different particles, and which is square of k, that is k square, and you take the square root, it becomes k. So this distance, or at this k distance, you keep a particle which is having mass equal to that of mass of our rigid body, and this distance k is called the radius of gyration. So its physical meaning is explained there. The radius of gyration of the body about the axis defined as distance from the axis of a mass point whose mass is equal to the mass of whole body. So this particle which you are putting here, which is having the mass which is equal to the mass of the whole body, and the moment of inertia of this is also same as that of our original body. Okay, so this is the distance at which you are placing the same mass particle whose mass is equal to the mass of our rigid body, and its moment of inertia about this axis of rotation is same as that of our rigid body. So at this distance where you are placing is nothing but radius of gyration. So the radius of gyration of the body about axis is nothing but a distance from the axis of mass point where we are placing this mass is the mass point, whose mass is equal to the mass of whole body and whose moment of inertia is equal to the moment of inertia of the body about that axis. Okay, the unit of radius of gyration will be, because it is k only, okay, so its unit will be, unit of radius of gyration will be meter, it is a distance, and its dimensional formula will be L1. Okay, now these are the different what you call it, theorem of perpendicular axis. Okay, the moment of inertia of a planar body, you try to understand a coin, you take a coin, you have two axes which are there in the plane of coin and one is perpendicular to the coin. Say this is your x axis, this is your y axis, and third axis is perpendicular to the coin. Okay, this is your say 1 rupee, 2 rupee coin. Okay, planar body. Now moment of inertia about the axis perpendicular to the plane, that moment of inertia if I take as Iz, and the moment of inertia about the axis which are there in the plane of this coin is say Ix, that is about x axis, and Iy, that is about y axis, then Ix plus Iy is equal to Iz. This is your perpendicular axis theorem. Okay, here it is yz plane is taken. Okay, so Iz, it is given here, Iz is equal to Ix plus Iy. A planar body is in yz plane. Okay, if you keep this as y axis and z axis, and perpendicular axis is your x axis, this is y axis, this is z axis, then moment of inertia about x axis will be Ix is equal to Iy plus Iz. And similarly, if you have say y axis as perpendicular, then you have x and z axis which are there in the plane of planar body, then this Iy is equal to Ix plus Iz. Okay, now this is a parallel axis theorem. As said, these theorems are not there in our course, but simultaneously I am explaining. It's very easy to understand. Say for example, you have a rigid body. This way you understand, so it will be very easy to understand. Say this is a rigid body. Okay, now say this is your axis of rotation. Originally you are rotating the rigid body about this axis of rotation, and this is your say z axis. Okay, now moment of inertia about this axis is say Iz. Now you want to just shift the axis, you want to rotate about this axis. So this is your another axis, say z prime, and the perpendicular distance you have to take that of the parallel axis. These are two parallel axes and you have to take the perpendicular distance. So these are two parallel axes. You have shifted your axis from z to z prime. Okay, now the distance between them is a. Perpendicular distance between these two axes is a. Now try to understand. Mass of this total body is m. Then the moment of inertia about this new axis, that is Iz prime, can be written as, try to understand, Iz prime can be written as sum of moment of inertia about original axis, that is Iz, plus product of mass and perpendicular distance between these two axes and square of it. So m a square, square of perpendicular distance between these two parallel axes. So new moment of inertia about that new axis is the sum of moment of inertia about original axis and product of mass and square of perpendicular distance between these two parallel axes. Okay.